So the simple analysis cases that we've gone over so far, in other words, the single loop circuit and the single node pair, show us a couple things. One, we can reduce any arbitrarily complicated circuit into a simpler and equivalent version that at least behaves the same according to a particular reference point. But also, in doing so, we've seen that we can combine elements. Resistors can be combined in parallel and series, likewise any other passive element, and voltage and current sources can also be reduced into simpler versions. But beyond that, these examples also lead us into using some useful analysis techniques that allow us to solve for specific parameters within the circuit rather than solving for all voltages and currents in the circuit. So the two examples that I want to talk about now are called voltage dividers and current dividers. Now this is a case where these are just kind of shortcut methods to help you solve for either a specific voltage in a circuit or a specific current in the circuit instead of solving for everything. If you don't know how to do these, don't try to force it. Don't use them everywhere you can think of. Just if identified and is clear to you, then this can be a useful tool. First, a voltage divider. A voltage divider occurs when elements are in series with one another. For example, if we have voltage source Vs being connected to a series combination of resistors, in this case the three resistors that we analyzed prior, we know that a single current Is is going to be drawn out of the voltage source and move through the three resistors. Therefore, each resistor will have a unique voltage drop across them, V1, V2, and V3. So we know we can just use KVL to solve this circuit, shown here, as done in previous examples. It turns out that as we go through this example, we'll end up being able to write any given any voltage, V1, V2, or V3, in terms of Vs directly. So this is one of those cases where you may end up remembering the formula for a voltage divider, for example, which could be useful and quick to solve. So to illustrate what the equation is, we start again with a basic KVL because that's how we solve a single loop circuit, sub in Ohm's law, and we end up with Vs equaling I times the summation of all the R's. Now at this point what we're going to do is, by noting that I can be rewritten or re-expressed three ways, specifically by relating I to any given voltage V1, V2, or V3. So in other words, I is V1 over R1 or V2 over R2, or similarly V3 over R3. We can sub those back into this expression that we obtained via KVL. So for I1, for example, or V1 rather, we can sub in the relationship that I equals V1 over R1 right into this expression, and we get Vs equals V1 over R1 times the summation of the resistors. Simplifying, we get V1 equals Vs times a fraction. We know that it has to be smaller than Vs because Vs is the only voltage source we have in this loop. And the fraction is given as R1 over the sum of all resistors. Likewise, we can do so for V2 or V3. V2 is just Vs times R2 over the sum. V3 is Vs times R3 over the sum. In other words, for the ith element voltage, Vi is going to be equal to Vs times R of that ith element over the sum of all resistors in the path. Simplest way to think about this is the voltage of the resistor we want is a fraction of Vs times the resistance that you're interested in analyzing over the sum of the path. This kind of thing works for capacitors and inductors as well, although a little bit differently. If we look at the capacitor case where we have N capacitors in series with a voltage source, again we start with the same basic KVL. Now when we do our substitution, we have the VI relationship for capacitors, which is 1 over C times the integral of I. Sum those up just as we did in the former module, or the formal presentation rather. And then going back and subbing in the individual IV relationship between the one that we want to solve out. For example, V1 being 1 over C1 times the integral of I, we get that Vs equals C1 times V1 times the summation of the reciprocals of the capacitance. And we can generalize this by saying the ith voltage of the ith capacitor is Vs times a fraction that is given by 1 over that capacitance over the sum of the reciprocals of the capacitances in series. This shouldn't be a surprise because of how we found out that capacitors are combined in series. They are combined in a like manner with the reciprocals. And resistors, as we found out, were combined by just summing the resistances themselves. And likewise, for N inductors in series, we can combine them as well. I'm going to not go through the formal proof for that. You can leave that for an exercise for yourself. The solution looks very similar to the solution we get for resistors, which shouldn't be surprising as well because inductors combine just like resistors do in series. They just sum up. So we see that the ith voltage across the ith inductor is Vs times that ith inductance over the sum of the inductances. Okay, so the next technique is called a current divider, and this occurs when elements are in parallel, where we noticed that what's interesting about this circuit is not that the voltage across every element is the same. This is powerful to know, but because they're in parallel, the current is going to be split into N paths. So for example, if these 3 resistors in parallel are driven by this current source IS is split into 3 other currents, I1, I2, and I3, which sum to equal the source, given by our KCL expression. So when we take this and then sub in our Ohm's law expressions, we end up with our KCL looking like Vs times the sum of the reciprocals of the resistance. And just like we did for voltage dividers, we note the VI relationship for any individual element. So in this case, Vs is also I1R1, or I2R2, or I3R3. We can sub any one of these back into this expression for where Vs is present and get an expression for any individual current by itself. So we can rewrite I1, for example, as being Is times a fraction given by 1 over the resistance of that path divided by the sum of the reciprocals of resistance, in other words, conductance. So we can write this one in 2 different ways. The ith resistor current is Is times 1 over Ri over the sum of the reciprocals. In other words, it's the conductance over the sum of the conductances. So this looks similar to the way capacitors in series work. So resistors in parallel combine in a like manner as capacitors in series. And finally, without deriving that explicitly, we can do the same thing for capacitors and inductors that are in parallel. Let me just make a note here that these are in parallel. But capacitors in parallel combine as this expression shown here. I of the ith capacitance in parallel is given by Is times the capacitance you're examining over the sum of all capacitors, and this is because capacitors in parallel sum. Inductors, the ith current through the ith inductor is given as Is times 1 over L of the ith inductor, divided by the sum of the reciprocals of the inductances in parallel, as this is how inductors combine in parallel. And finally, I've put together a recap slide for you where we have derived the analysis methods for solving for single loop circuits and single node pair circuits. From this, we found that we can reduce voltage sources that are in series by summing them together. We can reduce current sources that are in parallel with one another by summing them together. And we can reduce passive elements that are in series or in parallel by the methods shown in this slide. So study this slide, make sure you could reproduce it on your own. Don't just memorize the slide, but see if you can figure out how to come up with these expressions on your own to really test your knowledge of being able to do this.